And before we start recording today, or I am recording today, but before we start the lesson today, let me make this last couple of announcements from about the end of the term type stuff. Number one, most important, I hope you hear this before tomorrow, the end of the day tomorrow. Tomorrow is the last day to withdraw from a class. Withdrawal does not hurt you academically at all. It may have financial aid implications, and the only academic implications, it may put off your graduation. But failing or making a D in a course is going to put off that graduation just as easily and actually hurt your grade point average. So actually it's more advantageous to you academically to withdraw than to either fail or make a D. However, financial aid, if you've already taken a course, if you're taking it the second time, then they will not pay for you to do it a third time. You can either fail, withdraw, or make a D and retake the course once, and they pay for it. But if you've done one of those two things before, and then either fail, withdraw, or make a D a second time, they won't pay for it the third time. So, just want to get those two. So there's the first item. The second item, they have now opened student course evaluations, so please do those. And you'll do it for this course, but you'll also be asked probably to do one or two additional evaluations of something around the college, like food service or bookstore or library or registration process or something like that, advising something. You'll probably be asked to do at least one other survey, so please do those. They're very short. Generally, students tell me they take 5 to 15 minutes, so don't sweat it. Get it done. All right, good deal. Now, I can't remember. Last time we had this class, nobody was here, and I finished section 4.6, which was got through rank of a matrix and that type of thing. We had done that. And the test that I gave y'all, and this is one reason I wanted to say this here, and I tried to say it when the two of you picked it up early. There may be another question or two. I think the test only goes through nullity, doesn't it? Nullity? I think that's the last question. It doesn't do any, does it have a question on rank?
Number 9 is on nullity.
But no rank?
Determine whether the set's a basis. Determine whether the set spans.
Right. Okay. So you'll probably have an additional question or two, probably just one, that deals with rank as well as nullity. There, yeah, on this one, on the last part of this test. People came to me ahead of time asking, and this is what I had made up from previous terms, and I'll add another question or two to complete this last test. Okay. Yeah, and yeah, I'll try to do at least one more, and that'll cover rank. Because I believe section 4.6, see, 4.5 covered basis and dimension, and dimension was mentioned there in basis, right, on the test. Okay.
Determine whether it says A spans R3, B is linearly independent, and C is a basis for R3. And then the next one is determine whether this set is a basis for M2.
Right. And then something about null space or nullity.
And then null space, nullity.
Okay.
Number 9 has the rank.
Oh, it does have rank. Okay. Okay, well then there may not be a need for that, because 4.6 was dealing with rank of a matrix as well. And it had null space and nullity, right? And dimension, did you say dimension was mentioned?
Dimension was
Mm-hmm. Okay, so the last question may deal with that. Okay, 4.7 is talking about coordinates and a change of basis. And I don't think there's anything in the course description that included this. So I'm real.
Your Math 112 just uploaded, by the way.
Oh, did it?
Yeah, I get notifications when you're having videos.
Why did you get one?
Because I subscribe.
Huh?
Because I subscribe to make it easier
Oh.
to find you.
Okay.
So.
For tutoring purposes, or?
No, for like if I needed to find a video for class.
Oh.
Because I can just, if I have you subscribe, I can just click on the side there and all your videos.
Oh, all
instead
my.
of trying to search for
Right.
it.
Okay. Got it. Okay. Then there's applications of vector spaces, which is 4.8. And
Are you going to try to add these two sections into the test?
no, that's what I'm saying. I may just add the one thing about dimension, one question about dimension, but I don't think I'll add anything about those last two sections because I don't believe anything there is pertinent to, is on the course description.
So we're going to go to chapter 5 then?
Yeah, chapter 5 is inner product spaces. I know that was on there. And guess what inner product spaces deal with? Inner product is the same as dot product. So you're having it again, okay? So there's nothing too new here for some of you, okay? So chapter 5 is inner product, inner.
Be a little bit different.
A little bit, yeah, for sure. So we'll start this in 5.1, length and dot product in Rn, okay? So now we're going to be in real number system, not just one space, which is the number line, or two space, which is a plane, or even three space, which is space, but any size space, Rn, and talk about length and dot products in those. Whereas probably before now, you probably limited yourself to either two space or three space. Now we'll be talking Rn. So that's a little bit of a difference, but not a lot.
Good old 17 space.
Yeah, we probably won't do many of those, but all right. So, section 4.1 mentioned the vectors in the plane are directed line segments characterized by two quantities, length and direction. That's what a vector is. In this section, R2, the plane, will be used as a model for defining those and other geometric properties, such as distance and angle. Okay, distance sounds a lot like length to me. Angle sounds a lot like direction to me. Okay, so it's nothing too new. Vectors in Rn. Okay. In the next section, those ideas will be extended to general vector spaces. Then we'll get into polynomial and matrix and functional and other vector spaces. So this section will be in Rn. You will begin by reviewing the definition of length of a vector in R2, and that's a pretty simple process, and I think it's review for everyone, but just in case it's not, and since two of the three are not here, I'll do it. Here's a vector V. Let me get my pen. Yeah, sort of leading to that way. We'll get to the definition in a minute. Just a little before that. The vector V is the vector, and I'm going to try to put the angle brackets here, though this book doesn't use them. V1. Yeah, second. Yeah, I made out that a while back before this term, so I didn't. I just did what the test bank had. Okay. There's our vector V. Okay, in R2. Then the length, and here's the other thing. We probably talked about length and distance before. Now we're also going to introduce a new term, the norm. And it's not the one that they all yelled norm when you walked into the bar on whatever show that was. Okay. of V is denoted by the magnitude of V. That's the word I usually use for it, but this is calling it the length or the norm. All mean the same thing. And of course, what is that? That is the square root of V1 squared plus V2 squared. Okay? Now, this definition corresponds to the usual concept of length in Euclidean geometry, where we're used to living. That is, magnitude of V is thought, or norm of V, or length of V, is thought to be the length of the hypotenuse of a right triangle whose legs have lengths V1 and V2, magnitudes V1 and V2. As shown in the figure that you see there, and it's just simply this one. If you have two space here, and you have a vector here, then, and this is vector V, and the magnitude of that vector V is the length of the hypotenuse of, this is V1, let me make sure, yeah, magnitude of V1, this is magnitude of V2. Okay. Now, why do they express these as magnitudes here? You don't have to, because you don't square them, so you could have these as positive or negative. They're making the absolute values, which is fine. It still works out the same. But it's not necessary to do that. That's just the way they're expressing it. Okay? And since you're going to square both of those, and in fact, if you did this, the magnitude or norm or length of V squared is then V1 squared plus V2 squared. Okay? Now they put the extra term in there, absolute value of V1 squared, V2 squared. Why? It's just not necessary to put it there. Now, what you are saying, the definition, now the length of a vector is also called the magnitude. If the magnitude or length or norm is 1, then it's a unit vector. Just going back to that. So generally for Rn, it's no longer Pythagorean theorem, except it's Pythagorean theorem repeated several times, really is what it gets down to. But then the length, I guess I'll clear this. Okay. And say the length or the norm, again, there use those two terms. I also use magnitude of a vector V, but this time we let the vector V be in Rn. V1, V2, V3, dot, 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 all the way up to and including V sub n. Okay? Well, then what is the length of that vector? And this, by the way, is an element in Rn, because you have n components, is given by the magnitude of V, the norm of V, the length of V, is equal to the square root of V1 squared plus V2 squared plus V3 squared plus dot, 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 all the way up to and including V sub n squared. Okay. All it is. Okay. I think just what you would expect the logical extension of two space to be. And the reason I say it's repeated application of the Pythagorean theorem, I'll just show you in three space. So let's say you had a V1 here, some V2 there, and a V3 here. Well, if you do V1 squared plus V2 squared, square root of that, you're going to have the magnitude of this one. Then that one squared plus this one squared gives you another right triangle here. And then if you can picture that for up to n space, you're just doing it one more dimension at a time. I can't go past 3, so I can't even imagine past 3. But that's what the rule is. This definition shows that the length of a vector cannot be negative. Magnitude cannot be negative. That's sort of, I think, why they introduced the absolute value in there. Absolute value cannot be negative. Okay. So the magnitude of V is always greater than or equal to 0. And when is it equal to 0?
When is that equal to 0?
When what?
When is that equal to 0?
Yeah.
The whole thing is 0?
Yes, when you have the 0 vector. That's the only time the magnitude will not be positive, is when you have the 0 vector, which to me is a pretty innocuous vector. Okay. All right. And that's what they say in the next sentence. I didn't know they were going to say it then. So let's do example 1. In R5.
Let's say they said it was kind of a pointless vector. No, they didn't.
What's that?
I said they said it was a pointless vector. And it's like, no.
All right. Here in R5, I can't write well. Here is your vector V. 0, -2, 1, 4, -2.
That is a 5-space vector.
A 5-space vector. Okay, what's its magnitude? Yep. Yep. Magnitude 5. Okay. In R3, what's this one? Uh, 2/√17. As soon as I see that, I think this may be going to be a unit vector. Minus 2/√17. And 3/√17. And root 17 goes through on the out. No, I'm just kidding. Okay. Just making up something dumb. Okay, what's its magnitude? I think is what it's asking for. Yeah. I wish they'd have given it a different name. Same problem, just, okay. The square root of
4/17 plus 4/17 plus 9/17. 4 plus 4 plus 9 is 17.
So indeed, this is a unit vector.
You just don't have to.
Yeah. All right. Because its length is 1, that second V, the B part there, is a unit vector.
Well, this whole section is going to be like this, I am okay.
Okay. Each vector is the standard basis for Rn has length 1. It's called the standard unit vector in Rn. It is common to denote the standard unit vector in R2 and R3. I think you know these. In R2, the standard unit vectors are Ij, where do they list it? Yeah. These are 1, 0 and 0, 1. Okay?
If you want to go this way, just add K.
Yeah, if you're adding K, then you would add, then you have 1, 0, 0, 0, 1, 0, 0, 0, 1. That's really being lazy, isn't it? And they should have been angle brackets also, but I was doing what the book did. Okay. Two non-zero vectors U and V in Rn. Here's another definition. Let's get our concept, I'll say. Two non-zero vectors U, V, not zero vectors, okay? Neither one of them. In Rn are parallel when one is a scalar multiple of the other. If U is equal to some C times V.
They could even be on the same line, couldn't they?
What's that?
They could even be on the same line, couldn't they?
Yeah, definitely. They could be, sure. But they're parallel if remember, the vector doesn't matter where it's located, as long as it has the same magnitude and same direction, it can be anywhere. It doesn't have to be.
And changing the scalar doesn't change the magnitude or direction.
It changes the magnitude, but doesn't change the direction.
Right, it doesn't change the direction.
Yeah, and it doesn't change direction, so therefore it remains parallel. Exactly. Now, moreover, if C is greater than 0, if this thing C is greater than 0, then it goes in the same direction. U and V have the same direction, so that's what that's saying.
Because if it's negative, they have opposite.
Yes.
If it's 0, then 0 vector, but it can't.
Right. Yeah, and that's the only thing. For C to be 0, then it would be, then that would say that the 0 vector is parallel to any vector, which I just about as soon not say that. So let's see.
It just did not say that. Well, they say it can't be 0. They can't be the 0 vector.
Okay, they say if C is greater than 0, then they say if C is less than 0, then opposite directions, and they never mentioned that C could be equal to 0. Okay. I figured it was going to do that because I hit it real quickly. Now,
but yeah, they initially say that it can't.
Where did they say that?
0.
Oh, U and V can't be 0.
Right.
Yeah, so if both of them, then C couldn't be 0 too. Okay, got it. Okay. Now, theorem 5.1. Length of a scalar multiple. Let V, let me go and do it on a clean page. Okay. Be a vector in Rn. C is a scalar. Okay. Then the magnitude of CV, that's correctly a veta, okay. How long is it? It's the absolute value of C, because C could be negative, times the magnitude of V. Okay, you have to put that in there because obviously magnitude can't be negative, even if C were negative. But if C were negative and you did put the absolute value on, this magnitude can't be negative, then you'd have a positive equal to a negative. It can't happen. So you have to put absolute values on that. Okay. Got it. And their proof is okay. I mean, you're just multiplying. You first define what this is. If
You basically do the magnitude.
right, and then factor out the C. Yeah.
Say you're multiplying by an absolute value of C.
Right. Exactly.
It's like,
Okay. That's 5.1. 5.2. Unit vector in the direction of V. Okay. I think you've probably seen this before. If V is non-zero, okay, in Rn, then U, now this U is not a generic U, it's a special U. It happens to be a unit vector because of its definition. It's the vector V divided by the magnitude of V. Okay? Now, and that's obviously in the same direction of V, but it's just divided by its magnitude. Otherwise, normalized is sometimes they'll refer to it, making it a unit vector. It has the same direction. Okay. So unit vector in the same direction. Length 1. Okay. Your unit vector in the direction of V. Okay. And Here they do it. I was wondering if they were going to say, the process of finding the unit vector in the direction of v is called normalizing the vector v. Okay? And this is one reason, even though I understand why, when they are calling the magnitude of v, the length of v, they call it the norm of v. In my mind, the bells go off saying, you've normalized v. That's not what norm means. Norm means length. Okay? To normalize it means to give it length 1. So I shouldn't have ever said it, because now what I don't like about it, you probably will get confused by it, or maybe not. Okay. So that's called normalizing a vector. I like to call it that because you call it that in statistics and all sorts of places. So I'm glad they mentioned it here. So how do we find a unit vector? Find the unit vector in the direction of, I think I'll go to a clean page, even though we really don't need it, but just gives them more room. A unit vector in the direction of v, where v is the vector 3, minus 1, 2. Let me ask right now, is v a unit vector? Absolutely not. I mean, those three numbers are, each of them 1 or greater, and when you square them and add them to each other, you're going to get something much greater than 1. So, yeah, okay. So what you do then, once you've just done that, you in your brain, you just did this. You got that to be 14, right? 9 plus 1 is 10. Yeah. Yeah, the square root of 14. Okay. So therefore, the unit vector in that direction is then 3 over root 14, negative 1 over root 14, and 2 over root 14.
And see what's funny, I kind of got curious about the last problem.
Mm-hmm. Yeah.
See it, and I accidentally went through and did the squared each term, but I did it with the terms that were already squared.
Oh, I see. Okay.
Yeah. Way off.
Yeah. Okay. So, yeah, that is the unit vector in that direction. And then you show it is by squaring each of those and adding them together, and that gives you 9 over 14 plus 1 over 14 plus 4 over 14, and that gives you 14 over 14. Yes, you completed the loop, you might say. Run around in circles. All right. Now, what do we mean by the distance between two vectors in Rn? Okay. Again, we'll start with R2 and do a distance formula there from analytic geometry. The distance between any 2 points is, and by the way, they mention here a woman, Olga Tolsky-Todd, born in what's now the Czech Republic. Back then it was probably Czechoslovakia, or maybe even something before that, because she was born in 1906. And I don't remember when Czechoslovakia was made a separate country.
I would almost say it has to be, but I'm not 100% sure.
I know it was Czechoslovakia at the beginning of World War II.
It was at World War I as well.
At the beginning?
It may have been the Austria-Hungary.
Yeah, that's what I was going to say. That World War I.
Where she was born in the Czech Republic.
Exactly. Because the Austro-Hungarian Empire it fell apart. It was falling apart before, but World War I did it in, and it no longer was.
And it was split up, and Hungary was this thing.
And I was thinking maybe Czechoslovakia was made into a nation then. So what it was before that may have just been part of the Austro-Hungarian Empire. I don't know what it was called then. But anyway, what is now Czech Republic, she became interested in mathematics. The interesting thing is, yeah, I guess most of her lifetime women were accepted. They were just rare in mathematics. There were people a generation or two before her, women couldn't even get a degree in anything, much less in mathematics. So she came along at probably a pretty good time and obviously a pretty bright gal. Okay. So the distance between 2 points in 2 space, this is your distance formula, looks a lot similar to what we've been doing. Yeah, now they're calling the 2 points U and V. These are points now, not vectors. Yeah.
The point minus the first term of the second.
Yeah.
And the second term, or the second point of the first term, no, second term of the first point minus the second term of the second.
Yeah.
Something like that. Squared.
Yeah. And the sum of that gives you the distance. Again, Pythagorean theorem, basically, is what you're using there. Now, in vector terminology, that distance can be viewed as a length of the vector u minus v. Okay? Okay? And I guess let's do it this way. Now, that's distance between 2 points. Okay. Let's just say we had a vector, and I think they call this one u, don't they? And that's not necessarily a unit vector. And this is a vector v. And what they're doing is letting the endpoint of this vector and the endpoint of this vector, since they both are originating at the origin, then this will be, they call it u1, u2. Now, the point is in parentheses. The vector would be u1, u2. And that's why I like angle brackets more, because you're talking about very similar things here, but one's a point, one's a vector. And this would be the vector v1, v2. But this point up here has coordinates v1, v2. As long as both of them have the origin there. So if you're looking at the distance between these 2 points, that distance, d, is exactly what we said. u1 minus u1 minus v1 squared. That would be the magnitude of this distance here, from here to here. No, that's not quite right. Well, I don't really like their construction here that much.
It would be this chunk minus that.
Yeah, and yeah, if you're chunking it, yeah, that's exactly it. It almost seems like what they're saying here is that has to be a right angle, and it isn't. I mean, but it does work out that way. That it looks like it's a Pythagorean, and it is very Pythagorean, but it's not. That doesn't indicate this has to be, even though mine looks like it could be hit pretty close to the right angle. For some reason, when I draw triangles, I have to work at making them not right triangles. I don't know why. I just, no matter where I put that, it almost always comes out very close. Yeah. Yeah. So anyway, but that's the, so the distance, definition of distance between 2 vectors. And again, I don't like this terminology. The distance between the 2 vectors, the vectors are those 2 line segments. Well, that's what, they're touching each other. Where are you talking about? You're talking about the distance between the endpoints of the 2 vectors. And that to me is very different from this. So, but this is how they're saying it. The definition of distance between 2 vectors. Distance between vector u and v is the magnitude. And by the way, u minus v, here would be u, negative v would be here, and the something maybe not quite long enough, something like that, and u plus negative v would then be that's u plus a negative v would be here, and this distance here would be the same as that distance there. So I wonder, why in the world are you making it so complicated? I don't know. But this is what the distance, the difference between this. And again, to me, they should be saying the distance between the endpoints of two vectors u and v in R to Rn is this. Okay.
The paper that I wrote about Bernoulli,
Yeah.
Jacob Bernoulli, found out that, I can't remember if it was him or his brother, I think it was Johann.
Yeah.
He was teaching and had been teaching L'Hopital.
Yeah.
And L'Hopital had gone to all these lectures, and then he wrote a book
Mm-hmm.
and included stuff that he like published.
Right.
The stuff that he
Under his name. Yeah.
Yeah, like indeterminate form.
Right.
0, 0. That was.
Yeah, L'Hopital's rule and that kind of stuff. He had learned it under Bernoulli, but then they named it after him because it showed up first in writing in his book. I don't think, if I understand the Bernoullis well, he was probably not a happy camper. Right? So, I mean, they fought with each other, so I can imagine what they do with somebody on the outside.
I feel like after what I read about them, the two brothers,
Yeah.
it was more of a constructive
Right.
competitiveness.
Right.
It wasn't as like hostile.
Right.
But it was like they kind of pushed each other to do more and more.
Right.
And that's kind of why they discovered and did so much.
Yeah. But then Daniel Bernoulli did Bernoulli's
They
principle
had 8 mathematicians
in their family.
in like a span of 50 or 100 years.
Right.
Like 8.
Yes. The math gene got passed around big time, you know. Found that in my pocket.
And what's funny is their dad wanted them to take up the spice trade.
Oh, really? Okay.
And if they would have done
What a
that,
waste. Yeah. That's, thanks for sharing things like that with me, because I want that kind of a wow moments to happen in the paper. Otherwise, they're a pain in the neck to do and for me to grade. I want something good to
I
come
tried
out of
to
it.
touch on some of those things.
Right. Okay. It says try verifying the following 3 properties of distance. Okay. Probably will need something on this screen, but I don't have room for it. The first property is the distance between vector u and v has to be greater than or equal to 0.
I believe it.
Yes, it would have to be by its definition.
You can't have
It's
a
a
negative distance.
it has to be a
0, then they're like
Yeah.
on top of each other.
above. It says this is the magnitude of u minus v. Magnitudes are always greater than or equal to 0. They can't be negative. Or it says it's the square root of u1 minus v1 squared plus u2 minus v2 squared. Okay? And guess what? That's a positive square root. It can't be negative, okay? You're adding 2 positives together under there, or at least things that are 0 or positive, because they can't be negative, and you're adding 2 things that can't be negative together, then taking the square root, a positive square root, no way that can be less than 0. It would have to be, okay? So, multiple ways to do that one.
I didn't mean to skip ahead and already said the second one.
Yeah, the second one too, that the distance between u and v is equal to 0 if and only if u is equal to v. because that's the only way you're going to get U1 minus V1 to V0 and U2 minus V2 to V0. Only way that could happen if they're the same vector, because U1 would have to be V1, U2 would have to be V2. Okay? And then the third one, that the distance between U and V is equal to the distance between V and U. Okay? Because the same line connects the 2 points, has to have the same length, and it doesn't matter which way you go, the length is always positive. It's always the positive of it. Okay. Now, let's do example 3. Okay? The distance between U, which is -1 minus 4, and V, which is 2, 3, what would that be? Square root of 9 plus, what in the world is that? That's a -4. Evidently the line did not come down. Okay.
Okay, so that would be a -1 minus 2 squared plus, plus or minus, plus a -4 minus 3 squared. So that'd be 9 plus 49.
Yeah. Square root of 58, I think. Yeah. Now, because I don't like taking minuses, well, I like starting with positive numbers, and then minus and minus is plus. I just did them the other way because we just showed that distance between U and V is the same as distance between V and U, so I just reversed them and did it, and it made it, I didn't have to think about negatives much. Okay.
Yeah, I had to kind of slow down for a second, like, whoa.
Now, we're going to 3 space. The distance between U, which is 0, 2, 2, and V, which is 2, 0, 1, what would that be? Three, exactly. Ah! I had it written but messed up the writing. Okay. And that's what they got. The distance between, let's go to 4 space. -3, -1, 0, -3. Four, 0, 1, 2. Yeah. Yep. Yep. And you could write that if you wanted to 2 root 7. How did they do it? Yeah, they did. Look at them. Okay. Now, again, when I saw the header of this section and said this is the 2 vectors, I was imagining they meant a vector here and a vector here that didn't ever intersect. What's the closest point of approach is what I would have said. And I thought to myself, they're jumping into a pretty tough problem right off the top. That's not what they were talking about. They were talking about, especially if they started in two space, only way you could do them is two parallel vectors in two spaces. You could talk about the distance between them, but any other vectors are going to intersect somewhere if they're not parallel. That's not what they were talking about. The distance between the endpoints.
Will get into the three space where are they closest?
I don't think so. That's why it surprised me they were going to do that here. I thought,
Yeah,
wow.
Like they do the same thing as we're doing now, but in three space. Start everything at the origin.
Yeah. And so you're
Very
talking
similar
about,
thing.
yeah, well, we just did 1 and 3 and 1 and 4. So I can't draw 4. Okay. Now let's talk about the dot product and the angle between two vectors. Okay, as if this is new to you, right? Define the angle theta, as long as theta is between 0 and pi, between two non-zero vectors u and v, and we're in two space. So let me go to a clean page. U is the vector, u1, v1, u1, u2, and v is a vector, v1, v2, okay, in R2, obviously. The law of cosines to the triangle that you get, now they said two things, two non-zero vectors. Now they didn't say they couldn't be parallel. That would have presented a problem with the picture. And but as long as they're not parallel, you can do this. And in fact, I think it even works if they are parallel, because then you get, well, the cosine of 0 is 1. So, okay. I think it still would work, but no. So let's draw the picture here. They're calling this vector u, and this one over here vector v. Okay. Now why do they put the magnitudes on it? I'm not sure, except they're going to be using that in what's coming up. And this angle in between here is the angle theta. Okay. Now this distance here, they put it as a dotted line, but I'm just going to put it as a pretty faint line. This is going to be v minus u.
How did you do a faint line?
I just didn't press down as far. Okay. I didn't intend to, but I just did it lightly, and it sure enough came out faint. And I thought, wow.
That's kind of crazy. I didn't know you could do that.
I didn't either until I just did it. Okay. Now let me make sure that that is correct.
I looked up and I was like, did he switch colors that fast?
U plus a negative v that would be it. No, I don't know why they did that. I would have written that as u minus v. They wrote it as v minus u. That is really u minus v. Just doing the vectors. Okay. What they said is absolutely correct, because v minus u and u minus v, the magnitudes are the same. But the vectors themselves is that one, I'm pretty sure. Let me make sure again. U plus a negative v. Negative v down here. So that translate it up there. Yeah, that would be that. So that would be u minus v. They're not using that, but they're saying it. Now, what they're, if you put the arrow on the other way, it would have been v minus u. So let's do that. And it took the whole thing out. Let me see if I can draw lightly again. Wasn't that light that time. This now is v minus u. I'm trying to get it the way they do. just so it won't be some other level of confusion. What's that? I don't know. It doesn't matter. They don't draw an arrow on it anyway. They're just looking at the magnitude. What they're telling you about the magnitude of this then would be the length between those 2 points. And of course the magnitude here would be the length between those two. And the magnitude here is V. Okay. And here's from the law of cosines, I don't know if you remember this or not, that, and this is not necessarily a right angle.
Although it does look right.
I know, I tried not to, but it's a little beyond 90, I think, anyway. The book actually looks very close to right angle, but not necessarily. And it says, say again? Yeah, this is if you remember from the law of cosines that any of the two sides, but they happen to use this one, the magnitude of V minus U squared is equal to magnitude, and why they start with U, I don't know. It doesn't matter. U squared plus magnitude of V squared minus 2 times the magnitude of U times the magnitude of V times the cosine of the angle theta in between those two segments there. What's that? It sure is. Seems like a long post city. Never mind. Okay. Now, they say expanding this and solving for cosine V. Now, what do they mean by expanding that? Okay. If you go back to, and again, why they did V minus U when before they did U minus V, it's fine. But this would be the square root. Well, you lose the square root because you squared it. Okay? So it would be, this would be, yeah. Did they give, yeah, they're using components. Okay. V1 minus U1 squared plus V2 minus U2 squared. Okay, you lose the square root, right? Is equal to, and this would be U1 squared plus U2 squared, right? Yeah. And this would be plus V1 squared plus V2 squared minus 2 times the square root of U1 squared plus U2 squared times the square root of V1 squared plus V2 squared times, I don't know if I need that, the cosine of the angle in between. All right. If you did this is V1 squared minus 2 V1 U1 plus U1 squared plus V2 squared minus 2 V2 U2 plus u2 squared. And that's equal to yeah, you remove, u1s. I was trying to figure out why I had them in there in the first place, plus u2 squared plus v1 squared plus v2 squared minus 2. Okay. Well, yeah, but what I was going to do is, I don't know if I need to or not, do the square root of the product. Because the square root of A times the square root of B is the square root of A times B. Yeah. Right? So if we did the product of those two, this would be the square root. This is u1 squared v1 squared plus, that would be u1 squared v2 squared plus u2 squared v1 squared. Yeah, so squared v2 squared plus u2 squared v1 squared plus u2 squared v2 squared times the cosine of theta. All right. Wow. But here you have a v1 squared, there you have a v1 squared. Here you have a u1 squared, there you have a u1 squared. Here you have v2 squared, there you have v2 squared. Here you have u1 squared, there you have a u2 squared. Okay? Now,
you probably rewrite that first part and just leave the second part written there, just recycle it.
yeah.
I don't even know if you need to do that though. You have two twos on this side of the thing, you can divide the whole thing by 2.
Okay. Why was I doing this in the first place? Expanding and solving. Okay, that's why. Okay. Yeah.
But yeah, you have negative 2's on both sides.
Okay.
Yeah,
Okay.
you're multiplying it by cosine, so you should
Yeah.
be able to.
Yeah, you can divide out a 2, 2, and a 2. Okay? And what that leaves you with is cosine theta from over there is equal to
You gonna make that a negative 2 or positive 2?
well, if I divided out a negative 2, then it would have gone out, and that left them positive. Okay.
That would be V1, U1,
Yeah, there's your V1, U1 plus V2, U2 divided by the square root of that, and that, as you just said, was this absolute value of U times absolute value of V. Okay, that's how they got it.
Yeah, we didn't have to write all
You
that.
didn't have to do the square root part. Okay, and that's exactly what they've got here. Now, the numerator in that quotient is defined to be the dot product of U and V. This thing right here is the dot product of U dot V, or V dot U. It doesn't matter which order. Okay, U1, V1. See, that's the thing. Why in the world did they do V first and then change it around and put U first? Okay, so here's the generalization. Okay, the dot product, and I guess I need to go to a clean page, mostly for the people without a book. one or more that may not have the book. The dot product of U and V, and this is in N space, okay? So here we have U, vector U being U1, U2, U3, dot, 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 all the way up to UN since we're in N space. Vector V is V1, V2, V3, dot, 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 all the way up to and including V sub N, because it's also in N space. The dot product between those two, U dot V, would then be no longer vector, scalar, the scalar sum U1 V1 plus U2 V2 plus U2 3 V3 plus dot 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 plus U sub N V sub N. Say scalar number, okay, with that. Notice that the dot product of two vectors is a scalar, not another vector. So, boy, this is going to be hard, isn't it? Let's do the dot product of these two. U being vector 1, 2, 0, negative 3. And V is the vector 3, negative 2, 4, 2. And what's U dot V then? Yep. What should it come up to? -7. Got it. Okay. Pretty straightforward. All right. Here's theorem 5.3. How are we doing on time?
We got 9 minutes.
9 minutes. We can do theorem 5.3.
All I've been thinking about for the last 30 minutes
Is eating lunch.
Yes.
Right. All right. You should have had another granola bar. Okay. Yeah. Here we have, because I'm thinking that way too, and I had one. Here we have three vectors, U, V, and W. Yeah. Are all vectors in Rn. Okay? C is a scalar. Okay? Then the following properties are true and equivalent to some extent. Okay? U dot V has to be equal to V dot U. And if you think about it, you're multiplying the corresponding components. It doesn't matter which order you multiply because multiplication is commutative. And then adding them together, it doesn't matter what order you add them. Addition is commutative, so sure, it didn't matter. These are the same. Okay? Second, this is another truth here. The U vector dotted with the sum of V and W is what? Yes, and that would be U dot V plus U dot W. Okay? Now first, we got to see if it makes sense. V plus W is a vector. V is a vector, W is a vector. Add two vectors, you get a vector. Okay? You dot that with another vector, same dimensions, of course, so they're all in the same space, then you're going to get a scalar. Well, this is a scalar. Vector product, dot product of these two, the dot product of those two are both scalars. Add two scalars, you get a scalar. So at least the type of number makes sense. If you wanted to prove it better, you could do this is V1, V2, V2, W1, add that, then dot that with this, and U dot V plus W. U1 times V1 plus W1 plus U2 times V2. Do all that, and then do the other side, and you'll see you come up with the same thing. Because you have a common factor of U1s everywhere. Okay, so that one's true. And like you said, that's a distributive property of vector multiplication over vector addition. Okay, number 3. Scale, need to be careful on that. Sometimes we call that scalar multiplication, but usually it's better to say dot product over vector sum. Okay. Number 3. That constant C times the dot product of U and V. Which one? This one? Okay. That's the same as CU dot V, and they put those in parentheses, which is the same as U dotted with CV. Okay. What's your, yeah.
Wouldn't be like a C being distributed out. Like, you couldn't do CU dot CV.
No.
That wouldn't be fair. But if you did this dot product and then multiplied the scalar you get out of that by C, that'd be fair?
Yeah. That's exactly what the left-hand side is telling you to do. And the right-hand side is saying, the middle side is saying, that's exactly the same thing if you had multiplied C by U first, and then dotted with V, and that would have been the same thing if you'd have dotted U with C multiplied by V.
I would probably do the left-hand side one.
Right.
Just do the dot product and then bring in the scalar.
Yeah. Yes, I think so. Because the reason you can't distribute in, then you would be multiplying C twice.
Right.
And then you have C squared, and you don't have a C squared here. Right. So you can only multiply it by 1. So therefore, this isn't a distribution issue because there's no addition in here.
Yeah.
It's all multiplication.
Right.
It's really more of a associative property, kind of.
Right. If it was U plus V, then it would be a distributive.
Yeah, exactly. Yeah. But this is sort of associating these two and then dotting with that one, or associating, commuting these two and associating this one dotted with that one. So this is more of an associative property than it is distributive.
It's almost right like CXY or CX times Y or
Yeah.
X times CY.
Yeah. All right. Yeah, that is not one of my favorites either. Okay. Number 4. V dot V is the magnitude of V squared. Okay? Both scalars. And
when you dot V by itself, you're squaring it effectively.
yeah, basically, yeah, that's what you do. You're squaring its magnitude because you can't square a vector, not with a dot product anyway. And what this means is V1 or V1 squared plus V2 squared plus V3 squared plus V. That's what this comes out being. The square root of, let's see. No, that's exactly what that comes out being.
Because
V1 times V1 plus V2 plus V2 plus 3 times V3. So it's V1 squared plus V2 squared plus V3 squared.
right.
So
It's exactly the same as that, but without the square root. That's why the square is.
Yeah, that's why the square is there. Exactly. Number 5. Last one of these. What's that? Oh, yes. V dot V is always greater than or equal to 0. Well, if you look at above, the magnitude of a vector is always greater than or equal to 0. When you square that magnitude, it's always greater than or equal to 0. So sure, this has got to be greater than or equal to 0. And it's equal to 0 if and only if it was 0 to begin with. It is the 0 vector. Okay, that's the only way it could have been. Otherwise, it's always greater than 0. Okay. And they do somewhat of a proof there. it says you can use a graphing utilities or software program to find the dot product. And they tell you that, so if you're wanting to get that programmed into your computer or calculators, you can. All right. How are we doing? Have we got time for example 5?
We have 1 minute.
1 minute. Probably not. So we're going to start with example 1 next time. Example 5 next time. And goodness gracious, this is a longer section than I thought it was. What you can do is 1 or 3 or both, 5 or 7 or both, 9 or 11 or both, 13 or 15 or both, 17, 19 or 21 or both, and any of the odds 23 or 25 or both, and I think you can do 27. If not, you can wait until next time to do that. Yeah, you can wait till next time to do it. All right. And in fact, 23 or 25, if you don't want to try them now, you can do it. That's going to be what example 5 is. All right, good deal.